Swayam Prabha. Digital India. Educated India.
So the first two modules relating to PCA, we talked about a random vector. Either I know its probability density function, or I do know at least the first two moments. That's a purely probabilistic analysis. Now I would like to be able to transfer this knowledge to analysis of data sets. Analysis of data set which are represented in the form of a matrix. So I would like to give you an introduction to where do data matrices come from. So that is the goal of this module. Why data matrix? Please understand, data comes from various forms and shapes. One form is time series, IBM stock price, the maximum temperature in the city of Madras, daily maximum, the annual average, the total annual rainfall in the city of Madras. These are time series analysis. So time series is one form of data. Second is a spatial data. What is the total amount of rain that the state of Tamil Nadu or any state within India got during the month of December, and month by month, state by state. So the total amount of rainfall across all the states in India during the month of December. That's a spatial distribution. Then there is what's called spatio-temporal. What is the monthly total rainfall each state within India for the past 50 years? Month by month for 50 years across every state across every state. So that's a spatial domain as well as a time domain, spatio-temporal. The next form is called the matrix form of data. So time series analysis or time series data, spatial data, spatio-temporal data, and data in the form of a matrix. Analysis thus far assumed the knowledge of the properties of random vector X. In real world applications, we don't know the second order properties of the random process we are analyzing. We only have access to the ensemble of realization of X through direct measurements. So earlier I assumed X, it means 0 and its covariance is sigma. Here I don't know what the covariance of X is, but I do know samples of X. So I have observed several different samples of the random vector X. I don't know its mean, I don't know its covariance. So that's called ensemble of realization. N different samples of the vector X. So the first step is to organize this ensemble of data in the form of a data matrix, where each column is a realization of the matrix of the vector X. So the starting point for sample-based analysis, PCA, which is also called empirical orthogonal function, starts with a matrix X. X has m rows, n columns is the m by n matrix. M could be very large, n could also be large enough. Here, each column represents an object. Each row represents an attribute or an object. So to get a clear understanding of the object and attribute, let us take, for example, humans. All humans look alike. Then among humans, we can say men, women. Among humans, then we can say, hey, he looks like East Asian, he looks like Indian, he looks like European, he looks like an African. So there are features that distinguishes different groups of humans across the world. How do we distinguish them? We look at certain features. The skin color, the facial structure, height, weight. So humans, we have a very good way of trying to identify features that enables you to be able to distinguish one object from the other object. For example, a cat from an elephant, a human versus an animal. So those are the features. So I'm now going to consider n objects. The objects could be an image. So what is an object could be? I am having n different X-ray images of the bone structure. Each of the X-ray images are represented. An image is a two-dimensional structure. I'm going to represent and collate and convert the two-dimensional structure into one-dimensional structure. So each column refers to an image. It could be a human face. It could be an X-ray image. It could be object, could be, as we talked about, different human beings across the whole world. So objects versus features. An object is represented by a column. Features are going to be elements of that column. So every object is measured against the same set of features. The number of features is m, the number of is n. This is what we are going to be given. We can think of this as realizations of a random vector x belonging to Rm. The jth column is represented by x star j. The first star refers to elements along the rows, element along all the rows of the jth column. That tells you the profile of the jth object. The ith row refers to the values of ith attributes across all objects. For example, what is the weight of the n people I am considering? What is the height of the n people I am considering? What is the eye color? What is the educational status? So I can cut across the matrix either column wise or row wise. So this is called x star j. This is called x I star. Star refers to all the elements across the row or a column. Xij is the ith attribute of the jth object. Please understand, the first index refers to the attribute, the second index refers to the object. So Xij refers to the ith attribute of the jth object. Now some more examples. The object can refer to n students in a class. The m attributes can refer to the grades in the set of m courses taken by each student, each of the n students. So let us say I assume n is 5, m is 5, n is 40. There are 40 students, each of whom take 5 classes. The same class 1, same class 2, same class 5. So what is the entries in the table? Xij is the grade of the jth student in the ith course. Xij is the grade of the jth student in the ith course. So this could be a matrix that consists of tables of all the grades of young students in a particular department. Young students each taking the same set of young classes in a department. Second example is classification of humans. I already alluded to that. The object could refer to a set of young humans. Attributes may refer to height, color of the skin, weight, length of the torso, education, head size, color of the eyes, blood group, and so on. This is another technical example. In physical sciences, we are going to have models that describes the evolution. For example, in meteorology, we have models that describes the motion of hurricanes or typhoons over the sea, various types of seas. We can have one differential equation. I can run this one differential equation by picking n different initial conditions. Each initial condition makes the model different. So I can denote the n objects to be the n initial conditions for a class of models. The attribute may be the solution of this differential equation in a two-dimensional plane. So that means there is a two-dimensional plane. There is a typhoon sitting in here. I want to be able to see whether the typhoon moves here or moves here or moves here. I want to be able to understand the motion of the hurricane. There are partial differential equation PDE that describes the motion. For example, the region could be a Bay of Bengal. The depression happens and they generate typhoons. The typhoon wants to be able to move. I don't know exactly what are the initial conditions that led to the formation of the low pressure system, but I guess there are a set of initial conditions from which they could have developed. So I'm assuming there are n different initial conditions. So my matrix, each column corresponds to the solution of the PDE over this two-dimensional space, and the solution is given by the column for that particular initial condition. If I change the initial condition, I get another column. Each of these columns are going to be representing the solution of the same differential equation starting from different initial conditions. The reason is I'm quite uncertain about the exact condition that led to the formation of the low pressure system, which then intensifies and moves towards the eastern coast of India, and that's what I would like to be able to model. So what is the solution space? The solution space is a 2D structure. The solution space in this 2D structure, I'm trying to solve this partial differential equation by applying a grid in here. So if there are n points in this direction, if there are m points in this direction, the total number of points is nm. So I'm sorry, this is nx, this is ny, sorry, this is ny. So my m is equal to nx times ny. So there are m number of points, 1 to m. There are n initial condition 1 to n. So m is mx or nx. You can say mx number of points in the x direction and my number of points in the y direction. So the two-dimensional model is solved over the two-dimensional space consisting of m grid points. So this is a technical example, but is nevertheless a very good example where data matrix can arise from. The next problem, I'm trying to tell you the various sources of this data matrix so that we can understand where all the data can come from. In weather analysis, it is of interest to understand the variation of temperature of the height. In weather analysis or prediction, it is of interest to understand the variation is called geopotential, which is a measure of the height, Height is a measure of the geopotential of the atmosphere at different pressure levels. So what are the pressure levels? 900 millibar, 700 millibar, 500 millibar, 300 millibar, 100 millibar. At the ground level, it's 1000 millibar. As you go up, the pressure decreases. So we are going to measure height in terms of pressure. We know pressure decreases with height. So pressure can be used as a surrogate for representing height. So I have chosen 5 levels, 1, 2, 3, 4, 5. The pressure levels are 900, 700, 500, 300, and 100. The geopotential is defined by phi, which is the amount of work required to raise the unit mass from the surface of the earth to the height h. Please understand, the masses are being attracted to the earth, acceleration due to gravity. So if I have to raise something to a higher level, I have to do some work. The amount of work needed to be able to raise a unit mass from the surface of the earth to the height h is called phi of h, and that is called geopotential. It's a very simple idea from basic physics. So earlier, balloons with instruments for measuring pressure, height, temperature, humidity were hoisted from a given location. Once a day for 120 days, with 15 days before the start and 15 days after the given season, say winter in the northern hemisphere, for 10 successive years. Look at that now. I'm going to be, a season is about 90 days. There are 4 seasons. Each season is 3 months. 3 months is 90 days. But I'm going to observe the seasonal weather 15 days prior to the start, 15 days after the start, for a total of 120 days. So I have measurements for 120 days for each year for 10 successive years. Yam is the pressure level, 5. So N, 120 days times 10 years, which is equal to 1,200 days. So for 1,200 days, which are the objects, I have M features, phi, I have measurements of various quantities of interest, and that is what this diagram is all about. Let us say I have measured the geopotential. So now you can see I am going to have a broad matrix. This is 1 to 5, that is 1 to 1200. So this is the matrix of interest in meteorological, weather-related analysis. In climate analysis, say I'm talking about various areas of applicability of data science. To a data scientist, the data can come from any direction. A data scientist is a tool man. So there is a data collection part and the analysis part. The data collection depends on the area that you are working in. It could be bioinformatics, it could be weather, it could be climate, it could be images, it could be humans, it could be any other object. So you can see the generality of representation of data in the form of a data matrix. In climate analysis, we are interested in spatio-temporal distribution of sea surface temperature across the globe. We are interested in the distribution of concentration of greenhouse gases, the methane. For simplicity, we consider the 2D version of the problem. Pick a domain of interest and embed a uniform grid 2D with the mx number of points along the east-west and my number of points along the north-south direction for a total of m is equal to mx times my. And there is going to be a vector of size, x is a vector of size m is nx times my. Now I am going to describe this process with a simple example. Mx is 4 and my is 5, giving this to a total of 20 points. Points are labeled by 2 indices, p, q. P refers to the x-axis, p refers to the level, and q refers to the node at that node. So you can see there are 5 levels. There are 4 in here. So I can do this as 1 1 1 2 1 3 1 4. Likewise, this is called two double index representation. Nx is 4, mx is 5. But I would like to be able to collate this into one single vector x of size 20. To do that, for computing perspective, it is useful to number the nodes as a single index so that the data across the grid can be stored in a 1D array. There are two possibilities. Map PQ into a single integer. If you do the row major order, what is row major order? First row, second row, third row, go up. So bottom up, row by row. And each row goes from left to right, left to right. So go this way, from here to this way, from here to this way. So go up, you collate all the rows, you get a vector. So I get a row major order. So the point P comma Q now can be inherits an index k, where k is p minus 1 times mx plus q. For example, if you go back to the previous, if you consider the point 33, I have to pass two levels because the third level, third point in the third level. So I have to cross the two levels. Each level has 4 points. So 2 times 4, 8. And then, and the given level, which is a consideration, I'm going to have 3 points. So 8 plus 3 is 11. So this point is the 11th point. This is the first point. This is the second point. This is the third point. 4th, 5th, 6th, 7th, 8th. So let me write that. 9th, 10th, 11th, 12th, 13, 14, 15, 16, 17, 18, 19, and 20. So each place has two numbers. One is a double digit, another is a single digit. So with this, I can represent either using two indices or using only one index. I can do it row major order or column major order. In the column major order is q minus 1 times my plus p. The row major order k is equal to p minus 1 times mx plus q. So pq can get an index k or an index x depending on whether I'm going to consider the row major order or the column major order. A grid numbered using this formulation is given the two-digit representation, double index representation on the left and the single index representation on the right. And I have talked about the conversion. 4, 3 corresponds to 15 and column major order 4, 3 corresponds to 14. So this example gives you a very practical situation. I want to be able to measure a geopotential at 5 levels over 1,200 days at the rate of 120 days per year for 10 years. Now you can readily see how the data matrix can be organized based on the data set you want. The number 5, the number 10 years, 15 days above, 15 days after, these are all specific choices. You may want to vary this. Why is this important? I want to be able to understand the behavior of the atmosphere season by season. So you can have one matrix for winter, one matrix for autumn, one matrix for spring, one matrix for summer. So this is called seasonal analysis of climate data. So I just want to provide this example so that you understand. So what is the basic idea that comes out of this? The basic idea that comes out of this is scientists and engineers working on their own problems, they may be able to collect data. As a data scientist, you are going to work with an engineer or a scientist. They set up experiments to collect data. Of course, they are bright and intelligent. They may be able to analyze data themselves, but you as a data scientist can work with them. So data scientist, I don't think is a separate person. It is the same scientist could be the data collector as well as the data analyst. So, I am talking about the data collection part, data organizational part, and we have already talked about the theory behind the data analysis, namely the principal component analysis. The next data comes from generation of a data matrix. Sometimes we may develop an algorithm. When you develop an algorithm, you need data to be able to test the algorithm. You probably don't want to go asking for data sets from different people. You may want to be able to generate data yourself synthetically. So, here is an example. So, I am now generating a data set over a grid, 31 points along the x direction, 16 points along the y direction, M is 496. I am going to pick a random scalar A1 with mean 0 and sigma 1 square, normal distributed. A2 is normally distributed, 0 sigma 2 square. I am going to pick an epsilon x comma y, x and y are x coordinate, epsilon refers to the noise, which is mean 0 and variance sigma 3 square. I am going to pick a time interval 0 to 100. I am now going to generate a two-dimensional field G1 x comma y time. So, there is a two-dimensional spatial variable x comma y and t is a time variable. The spatial variables are given by cosine pi x by 30, cosine pi y by 15. The time component is given by the amplitude, time component, spatial component, spatial component. G1 is one signal, C2 is another signal. So, this is called the spatio-temporal signal distributed in two-dimensional space and time. Now, I am going to consider a signal G, which is the sum of G1 and G2 and the noise component x comma y and t. X comma y and t is the noise. We already talked about the noise component. The noise component is again Gaussian. So, set t is equal to 1, generate A11, A21 by setting sigma square is equal to 0.6, sigma 2 square is equal to 0.3. X is 0 to 30, y is 0 to 15. Now, I can at time t1 I can get g1 x1 xyt x11, g2 xy1 and gxy1 is equal to g1 plus g2. So, we can obtain a column vector using the row major order. So, what is that? Here is mx, here is my, the total number of points. I have a grid embedded in here. I am going to have a row major order, the same way as we have done in the climate example. So, the row major order, I am going to get a vector of size 496, and because it is time t1, now I am going to have a matrix. At time t1, I am going to have a vector of size 496. So, this is 1, 2 up to 496. This is going to be various set of objects representing time. So, what does this tell you? This tells you the temporal distribution, the spatial temporal distribution at time 1, what is the distribution? What time 2, what is the distribution? At time t, what is the distribution? So, you can think of this as a spatio-temporal data which is synthetically generated using a specific mode of generation. There is two signal component and one noise component. So, the entire matrix is now, I am now going to consider the time interval 100 units, 1, 2 all the way up to 100. So, I have a matrix which is 496 by 100. At t is equal to n is equal to 1 to 100, repeat the above process. The above process was talked about for t is equal to 1. So, repeat that. I can sometimes use n as the column index. Now it's called t. So, t is the same as n, that is why I call it t is equal to n. So, I got the first column, likewise I get all the rest of the 100 columns. Clearly, each row represents the grid point, in each column represents an instant in time. So look at this now. What is an attribute? What is an object? There is no hard and fast rule. It is only limited by imagination. So the definition of the matrix X has lots of flexibility, and it is to induce and understand this flexibility. I am giving examples from various domains of applications. The jth column gives the profile of the variable of interest across the grid at time j. The ith row gives the distribution of a variable at all grid points across at that particular grid point across all time. For example, I can think of what is the maximum temperature at 12 noon in the city of Madras over the past 100 days. So the spatial domain is fixed. I am talking about the temporal domain variation. So Z was the signal, C bar is the data matrix. So I am going to consider a noise vector eta t, m is equal to 496 components. They are unrelated Gaussian noise. This could be capital G, Gaussian noise. And you have already seen the Gaussian noise is 0 mean and a variance sigma 3 square. I am going to assume the sigma 3 square is 0.2. So at t is equal to 1, you generate this vector. You have a Gaussian random number generator, and you get the Gaussian variable eta. You call it 100 times, you get a vector. I'm sorry, you call it 496 times, you get a vector. You add it to the first column of the signal, so you get signal plus noise. And repeat this for 100 times. Create a matrix of noise, which is m by n. Now create a data matrix, which is noisy. Z bar is equal to Z plus eta, where Z is obtained earlier, not T. Z was obtained earlier. So I generate the data matrix, I generate the noise matrix, I add the noise. Why? I want to be able to represent reality. And this is what is called the digital twin in modern times. I want to be able to mimic nature. So measurements consist of signal and noise, and I'm trying to model both the signal and the noise. The matrix, so noiseless and noisy data matrix. Z is 496 by 100 is the data matrix that represents 100 members of the ensemble of realization of a 2D field, x, y, t, defined in 3 by setting the noise to be 0. If there is no noise, so what is the field variable? The pressure distribution across the city of Madras at ground level. The pollution across the city of Madras at 12 noon. So T is fixed, x and y are varying. We can talk about, so such distribution are of physical quantities. The physical quantities are called a field variable. So it could be temperature, pressure, amount of rainfall in each of the grid points. It could be concentration. It could be many things of interest in applications. So Z bar is a data matrix of the same size with noise corrupting the signal. These two matrices will be used to develop or test the methodology. So as I told you, if you have developed an application, I want to be able to benchmark the application to understand the performance, the actual performance of an algorithm. To understand the actual performance of an algorithm, we want data from reality. One way to get reality into computation is to use the surrogate. The surrogate data is something that is generated in the laboratory by using mathematical functions and by generating the various fields and by generating noise. There is a very nice book by Eschel, Spatio-Temporal Data Analysis, Princeton University Press, that contains a very good discussion of several examples of spatio-temporal data using EOF, that means empirical orthogonal functions. So we are making progress towards ultimately understanding the data set. So, we talked about two different ways of analyzing the data using principal component analysis. Now, we talked about where do ensemble of data come from. Ensemble of data essentially comes from realizations of the random vector x. We may not know the distributional properties of x, but we have the facility to be able to observe. And by observing this over space and time, we can build quite a variety of matrices from different application areas. So, with this data on hand, now we are going to move on to doing what is called empirical orthogonal function analysis, which is essentially a PCA applied to data matrices. Thank you.